Okay, so I think today's talk will follow on quite nicely from what we heard from Alexander this morning, in that we're talking about reinforcement learning. But so my question this morning was the environment that he was looking at, specifically related to an image-based state, was kind of a motivating question for what I'm going to talk about, because we wanted to understand what is the source of reinforcement learning error, specifically in environments where the state is image-based. And this is joint work with two of my colleagues, Atefeh in Nokia, New Jersey, Ryo in Nokia, Cambridge. But it's not even contributions, because the vast majority of the work was done by two interns, Alihan Huyuk, and Xueyuan She, and they actually did it as part of two separate internships. So I'll say a little bit more about them when we come to the parts that they did. And I believe I just saw Alihan on the call. So hi, Alihan. Okay, so this picture on the top left, Alexander showed this morning. So it's the obligatory picture you have to have in any reinforcement learning talk. So reinforcement learning is where you want to learn an agent that will do well in an environment. So you have an environment which has a state at time t, and you have an agent that can take an action at time t, and then what the action does is it gives you a reward, and it will convert your state into a new state. So games are classic examples of reinforcement learning. So you have your state here, and this is going to be important for the rest of the talk. The state is going to be the image of the game here. So this is the classic Atari game Pong. And this is actually 4 different copies of Pong. And as I suspect most of you know, the goal is to control the paddles on the right-hand side in order to win the tennis game. And this is where we actually have 4 different games going on at a time. And reinforcement learning has been shown to give superhuman performance on games such as these. It would certainly be quite hard to control all those paddles as a human and figure out what's going on. So that's, as I'm sure most people know, is what reinforcement learning is. And then we have deep reinforcement learning, which is essentially the same thing, but the decision that an agent will take in any given state is actually driven by a neural network. So you have some policy that will actually figure out what's the right action to take in any state. So you feed the current state into a neural network, and you get an action out. And the other notion that we're going to use quite a lot is the notion of a Q value. And that really comes out of the Bellman equations, because if you want to find the agent that will, so basically the name of the game here is to find an agent that maximizes the reward. And it's known that one way to do this is that in any state S, you take the action that maximizes the Q value, and the Q value is the fixed point of this equation here, where you essentially say that, and you can think of this as the long-term reward of taking action A in any given state. And so this is defined as, so the long-term reward is basically given by, you can think about this comes from playing the game continuously. So you keep on updating this average estimate of the reward. So that's driven by this alpha parameter. So you can think of it as the fixed point of an equation where it's you take 1 minus alpha of the Q value, and then plus alpha of the instantaneous reward for taking the action in the current state, plus the long-term reward in the future after you take so this is the reward for okay, so this is the reward for taking action in a given state that will put you in a state S prime, and then you want to in the future take the maximum, the action that then maximizes the Q value for that new state. So in summary, this equation here, if you take the fixed point, you get a value, a long-term value for taking action A in any state. And what you want to do is always take the action that maximizes this. So the specific thing I want to talk about today is what happens when the state is represented by an image. And we're going to look at a number of different environments, but many game-playing environments, this is the situation. So, for instance, Pong, or this full-game version of Pong, you can have the you can have this image that represents the state of the four games. We're also going to look at a couple of maze environments. One that's a little more complex, where we have these four rooms and we want to drive an agent. So we want to have an agent learn how to navigate in the space and get to a target. So here, the state of the game is the image that represents this maze. And we're also going to look at a very simplified environment where the agent has to move up, collect a key, then move to a door state space, and then move to a target. And we now have some power. So what does reinforcement learning specifically look like when we have these image states? So generally, and when I say that the image is that the state is an image, I literally mean it's the RGB pixel values for the image. So you can think of that as what goes into the reinforcement learning. It's literally a vector of RBG values. And generally, the way RL works when you have an image state is that you'll have some encoder that gives you a representation of the state. So you can think of, so we'll have this notion of the observation, which is literally the input state that's given to you. But typically, what you'll first do is feed it with some sort of encoder that will give you a representation of the state, and you could think of this as, you know, saying, oh, okay, there's a yellow key in the top left and a yellow door at the top, etc., etc. So we get this representation of the space, and then you can take this representation and then feed it through another neural network that then gives you some output. And as far as I'm aware, most deep reinforcement learning algorithms have some structure like this. I mean, you could imagine just some arbitrary neural network that takes the input and spits out the action. But in general, there is a sort of, in the neural network architecture, there is a well-defined split between what goes into, between the, effectively the image encoding, and then you get some feature representation, which is then fed into a separate neural network. So with that in mind, we get the following question. Suppose your RL doesn't actually work very well. There's actually two potential sources of that. One is it the actual encoder? So you can think of the encoding as just a classic sort of computer vision problem, you know, nothing to do with action taking or anything like that. So it could just be that the computer vision part doesn't work very well, that somehow the encoder doesn't really understand the image correctly. So suppose you want to say, do blah if the image is a cat, blah if something else if the image is a dog. Well, maybe if you don't have a good discriminator between cats and dogs, then you can't do anything. Maybe the decision is easy at that point. Or maybe or maybe we can actually recognize the state really well, but we just can't take the decisions very well. So in that case, the decision policy is bad. Or is it some combination of the two? So I didn't want to put a video, so just apologies for people on the bridge, but I just wanted to motivate this problem a little bit. So the last time I gave a links talk here 2 years ago, I talked about various problems in robotics where we were essentially taking the LiDAR view of a robot and converting that into an image, and then creating using RL to create an obstacle avoidance algorithm. So again, this probably won't be very visible to people on the bridge, but we have a robot driving here, and we have an image representation, which is essentially a polar representation of the LiDAR of what's seen. So essentially, we have an image that is defining the state of what the robot is seeing, and then we wanted to use that to drive a reinforcement learning. So this was the motivation for the problem, is that sometimes the training wasn't working very well, and it was a priori very hard to figure out, is it just setting it up as this computer vision problem, which effectively the vision here is understanding the LiDAR representation of the robot. Is that the problem, or is it somehow we can recognize all the obstacles, but we can't do a good sort of planning of the trajectory? So that was one question, and then a very related question is how well does this type of structure generalize? So what we mean by generalization in the RL context is if the state space is perturbed, will the agent still get good results? So if we train in one environment and then we move to another environment, will we still get good results? And that's obviously very relevant in the robot context. You don't want to have to train the robot in every room is going to work in. You want to train it in one environment and hope it knows the concept of obstacles and doors and these sorts of things, and will it go to the right place? So compared to the literature on sort of general AI generalization, as far as we can tell, there's much less of a literature on reinforcement learning generalization. But from the references that we did find, I think the general conclusion is that oftentimes RL doesn't train very well. It doesn't generalize very well. So what does that mean exactly? And it really depends on what you mean by moving from a sort of training space to a test space. And mostly we're going to talk about two notions that are somewhat different. I think they're both very reasonable, but so I think that's another sort of takeaway here, is that generalization can actually mean different things to different people. So there's a nice paper of Zhang et al. Where their notion of generalization is typically in these environments, you have some sort of random seed that will generate your environment. Maybe it generates a maze or something like that for the robot to go through. Now, the state space is therefore defined by the random seed that generates the environment. So generalization means here, you've got a set of seeds that you train on. What happens if you move to a new set of environments defined by a different set of seeds? So that was one notion of generalization. Song et al. Looked at a different notion, which is they were saying that typically when you have a state, you have information that's relevant, that's maybe that says where the obstacles are in a robot environment. Then you have irrelevant information, like say the color of the obstacles. And their notion of perturbations was, what happens if you change the irrelevant information? Do you actually still get decent performance? And they had a very nice example of that. So they looked at some game playing examples, and they actually noticed that sometimes what the agent, so it's known that for a lot of these video games, if you train an environment, you just keep playing the same game, it trains very well. But one thing they noticed was that sometimes, because you can kind of look at what areas of the image are most affecting the neural network, they found it was actually the timer on the screen that was actually driving the results. So it had nothing to do with learning to play the game well. It was literally just looking at what's the time of the game, and it learned at this time of the game, I should take action blah, and then was getting good performance. But that's obviously a completely stupid way of playing the game, because you could start at a different point, the timer could be off, and then things would be very different. So their way of describing this was saying that image-based RL is prone to observational overfitting. So it overfits to the observations where there's some salient information it should pay attention to, but it's actually paying attention to something else. So basically, what we wanted to do, therefore, is really sort of try and answer these questions. So how much of the error is due to the image recognition being bad, and how much is due to the decision-making being bad? And separately, we wanted to tie this into how well does the model generalize. So we worked on this. We worked on this problem with 2 interns. The first was in 2021, Xueyuan She, who came to us from Georgia Tech. He's now working for Amazon. And in that summer, we looked at the problem in the following way. We really asked the question, how well can we teach an agent the best action for each state? Because we felt this would be a proxy for the difficulty of processing the image state. So let's just actually move away from it being an RL problem. Let's say, okay, let's suppose that we have an oracle that provides you the Q function. So the Q function, remember, is basically says, what's the long-term reward for taking action A in state S? What happens if we provide that by an oracle? So in short, we basically did 2 things. So the first was we ran the RL agents as normal. We just ran the system to iteratively solve the Bellman equation as most RL algorithms fundamentally are trying to do. But we also just had a one-shot deep neural network where we were literally just trying to learn the Q function provided by the oracle. And we had 2 notions of this. One we call the regression task, where what we're trying to do is directly approximate the Q value for each state and action pair. The second task we call the prediction task, where we're not trying to predict the Q function directly, but we're just trying to predict the maximum action. So the output of the network is basically what's the best action to take. And I'm just basically just going to be showing a few results here. So for this particular study, most of the time we were looking at this particular environment, which was just this maze environment where we essentially have 4 rooms and the agent has to look at here, figure out where the doors are, and then as quickly as possible get to the target. There are variations of this where you actually only have a limited knowledge of you only know the environment within a certain distance, but we were actually looking at it where we just give this entirely as an image. So this is obviously something quite simple. You're just trying to learn from this image what's the shortest path through the doors to the target. So what you can do there is for each state, you can essentially create a vector field which tells you ultimately for the decision that you're making, what's the direction that you're going in. And the length of the arrow here means sort of the discrimination between the different directions. That in some states, it may not, the optimal answer may not be going in any direction, in which case there's no real vector. But when you're near a door, then there's a clear right direction in which to go in. So we have the top middle here, the ground truth vector field. This is what the agent should do to get to the target for this particular environment. So the state here is basically which point of the maze you're in and which direction you're pointing at. Blue here, I'm circling 2 actual RL agents. So these are trained by either the deep Q networks algorithm or the PPO algorithm, 2 very classic RL algorithms. And then here we had the outputs of the deep neural network that was trained for the regression task, where we're directly feeding it Q values, and here we're just feeding it the right action. And we took a number of different environments, and we gave we trained it with the with the correct Q values for all of these. And as you can see, this sort of one-shot neural network worked really well. It more or less got exactly the ground truth, and whereas especially the PPO algorithm gave actually quite a messy algorithm. It gave quite a messy vector field. But here, this is one of the environments on which it was part of the training set. So how well does it generalize? What happens if we give it an environment that was not part of the training set? So an untrained environment. Well, again, you get these quite messy vector fields for the PPO and DQN, the actual RL algorithms. But for the ones where we did the one-shot training, you can actually see that it's not actually working so well in that, for instance, here it's telling you to go up, where in fact the door is not there anymore. So what this is showing is that, so if we go back to our original question, how well can we train a one-shot neural network just to do the image processing if you give the ground truth values of the Q network? The answer is you can actually learn that really well, but it doesn't generalize very well to unseen states, and the actual RL agents seem to do a better job of generalization. Now, I think one question that we couldn't really figure out is how much of the better performance really came to the sort of more random nature of the vector fields here. You know, how much does the sort of noise in the solution actually help for the generalization? But to give a sort of another illustration of the difference here, this shows essentially for a given starting point. So we have here on the left a trained configuration and two untrained configurations. We show via colors what's the probability of getting to the target within a certain bounded amount of time. And for the trained example, pretty much the one-shot algorithm and the RL algorithms all did pretty well. But for the one-shot neural network, so both the prediction network and the regression network, on the untrained examples, they definitely had worse success rates than the actual trained RL algorithms. So I think this was illustrative in some ways, but I don't think it gets to the full answer to the question. So certainly it means that if you essentially giving the Q values as ground truth, you can learn that ground truth, but it doesn't really do what you want to do because it doesn't generalize very well. But it still doesn't really get to the notion of, can we separate out the, can we somehow have a very formal separation between this notion of the error due to the image processing part of the RL and the actual action part of the RL. So, and in full disclosure, so when we tried to submit the previous work, that was actually the main reviewer comment that came back, is that this is a nice question to look at, but one really should try to actually formally define what's the split between the two different sorts of error. So that's what our second intern on this problem, Alihan, who came to us in our Cambridge lab, who's a PhD student at University of Cambridge. He's recently finished and he's just started a postdoc at Harvard. So we kind of gave him this problem again. So we'd given it to one intern, and now we were saying, because we felt somewhat unsatisfied with the set of experiments that we've done so far, can we try and more formalize this difference between the two sorts of error? And during his work with us, he came up with a a set of definitions that both got to the notion of the split between the error due to the image recognition and the error due to the decisions, and also gave some insights into the generalization error. Is the generalization error due to not recognizing enough information or somehow recognizing the wrong sort of information? So first of all, let's talk a little bit about the split between the two sorts of error. So for that, he was using the notion of regret. So I don't really want to go too much into all the notation here. I'll at least try not to, but at least at the beginning, I will try and say a little bit about what the notation is referring to here. So we're going to use big R for regret here. We're going to use rho and pi for RL policy. So rho is going to be the output of the encoder, is going to be the representation of our state, and then pi is going to represent the decision taken on that representation. So for a given algorithm, we're going to represent it by rho 0 and pi 0, and then the optimal algorithm will just maximize over each of those policies. We'll let E here represent the environment that we're working in, which will be important when we're distinguishing between the training and the test environment. So the regret here is just the difference between the maximum reward that we can get and the reward that our algorithm gets. So if we have an algorithm that uses policy rho 0 and pi 0, then the regret is going to be essentially the difference between the maximum reward that we can get and the regret that we get from our algorithm. So the first thing we want to do is actually try and split this up into the difference between the recognition regret and the decision regret. So the recognition regret is going to say, if we take our recognition policy rho, what's the difference between the best value we can get out of our system, the best reward we can get out of our system, and the best reward that we can get if we use this particular recognition policy. So if we decide that this is how we're going to, if our encoder here represents the state in a particular way, what's the best way, and we then take the best possible decision based on that representation, how well can we do? So that basically says how much are we losing due to this specific recognition policy. And then the decision regret is going to basically say, well, what's the difference between our decision policy based on that recognition policy and the best decision policy based on that recognition policy? So, so that gives us a sense of, well, how much does the error come from? Do we recognize the state well, or do we are we recognizing the state badly, or do we recognize it well and just make poor decisions? So it's, I think, a little bit, at least for me, it remains sort of confusing to think about this in the abstract. So let's talk about it in a little bit with an example. So can I move the zoom? That's here. So we're just going to look at a very simple three-state Markov chain here. So obviously what our reinforcement learning does is work on is effectively work on Markov decision processes. So you have a state, you can take an action in any state, and when you take the action, you jump to another state and you get a reward. So the salient features of this are, A, there's no probabilities here. The action entirely determines which state you go to next. And there's only one state that gives you a reward. When we reach state 2, then we get a reward here. So the so this is going to be our underlying Markov chain, but we're going to have a representation of this state, which is going to be an image state. So this is supposed to be an image that represents the numbers 0, 1, 2. And what will become important later is that we've got some colors here. In the top right, we're also going to have the timestamp of the state that we're in. And we've also put some fuzziness in here in order to sort of represent, okay, maybe let's make it a sort of slightly more challenging recognition policy. Okay, so if we have a discount factor of 0.9 here, so the discount factor is just how you discount rewards in the future versus rewards now, then you can solve this Markov chain and you get a value of 4.263. So let's look at a particular recognition policy and a particular decision policy. First of all, suppose with the recognition policy, we misidentify each state with a certain probability. So suppose with 10% probability, we actually misidentify, and we'll just assume we just assume we're in a random state at that point. So we've got this slight sort of interference in the image. So we're going to say with probability 10%, we misidentify our state. But then to define the recognition regret, we say, okay, based on that misidentification, so that means that we go to our sort of representation of the state. We might actually get it wrong. If we're actually in state 0, we might say we're in state 1 or state 2. So so if we make those mistakes in the recognition, but we take the perfect decision policy based on the even so, then it turns out that all we can get as a reward is 3.992. So that means the regret at this point is the difference between the optimal and what we can do with this recognition policy and 0.271. Suppose based on that recognition policy, we then have a decision policy which just takes a random action with probability 10%. So again, it's not doing the optimal thing. So I probably should have told you what the optimum policy here is. So we always want to go to state 2 as much as possible. So if you're in state 2, you want to take action 0 to get to state 1 so we can get back to state 2 as quickly as possible. If you're in state 1 or 0 or 1, you want to take action 1 to get to the right as quickly as possible. So, but let's suppose we take a random action with probability 0.1, then we'll only get a reward at this point of 3.68. So we're losing another 3.12. So our total regret between the optimal and the suboptimal situation, which comes from a suboptimal recognition policy and a suboptimal decision policy, is 0.583. So obviously the numbers are not so important. Maybe what's most important is to think of this notion of we can get things wrong both by misrecognizing the number and by taking a bad decision, even if we recognize the number correctly. So that's this more sort of formal definition of the first question I asked. How can we separate out the error from the recognition error to the decision error? The second question was about generalization, which is how well can we use similar notions to define how well an algorithm performs in modified environments. So we're going to look at that in this the same simple toy example, where the training environment is going to look like this, where we have colors on the numbers. But suppose we now test it in this modified environment where we remove the colors. Now you can still sort of see that's a 0, that's a 1, and that's a 2, but it's not so easy. But it's slightly different from the test environment. So we then get this notion of generalization regret, which is basically very similar to the notion of regret. And I don't want to go in detail through the equations, but it basically means the generalization regret is what's the value we get in our test environment minus what happens if we take the best algorithm in the test environment minus what we get in the test environment if we take the algorithm that was trained in some different training environment. So that difference is the difference that we get due to the generalization. And then again, without maybe going through to the details of the equations, you can then, just as we did before, you can split that generalization regret up into a piece that depends on that tries to get at how much we're losing due to a suboptimal recognition policy and how much are we losing due to a suboptimal decision policy. And once we have these definitions in place, we can formally define some notions that are reasonably intuitive. So first of all, what does it mean to overfit in this type of problem? Well, what it essentially means is clearly when you've got low training regret but high generalization regret. So the first version of regret I said was just in a single environment. So that basically says in that environment, how much do we lose by taking suboptimal decisions? This is about the difference between taking the right decisions in a training environment versus taking the right decisions in the test environment. So if we've got a low training regret, we can train well, but it doesn't move over to another environment, then we say we've got low training regret, high generalization regret, so we're overfitting. Observational overfitting is where we have overfitting, but the only difference between the two environments is in the recognition policy. So we're making the differences. So you can think of it as about we're taking away the colors in the numbers from the previous example. And then we can also define the notions of whether a recognition policy is being under-specific or it's being over-specific. So if the generalization recognition regret is high, but the decision regret is low, then that effectively means that the recognition policy can't get the right information from the system. So effectively, there's few features in the recognition to work properly. Conversely, if the recognition regret is low, but the decision regret is high, then maybe it means that we're picking out some irrelevant features in the recognition where the decision policy is honing in on those, and therefore, so it means that from the recognition policy, there was a right way to take the decisions, but we're taking the wrong decisions. So maybe the decision policy is looking at the wrong piece of the representation. Again, this is probably a little confusing without examples, so it's probably best to focus on the examples here. So we're looking at so suppose we have the as described before, the following training environment and test environment. So the training environment is our Markov chain exactly as it was before, where we have the colored representations of the numbers. And the test environment, as we take these away, then suppose our recognition policy was based on originally color. So suppose we trained in the training environment and our recognition policy, basically, it didn't look at the sort of pixels. Does that look like a 0? It looks like a 1 or a 2. It looks at the distribution of color. Clearly, that's not going to work in the test environment because we haven't teased out enough information to actually figure out is that going to we haven't teased out enough information to actually solve the problem correctly. So in that case, if we just work out the numbers, we get a recognition regret that's higher than a decision regret. However, if we have a recognition policy that's based on the timestamp, then that turns out to be over-specific. And maybe one thing I have said is we'll also assume that when we do the test, we don't necessarily start at the same place every time. We can start at our initial state could be different. So if our recognition policy is based on the timestamp, then we get things the other way around. So recognition regret is 0 in this case, because even if you kind of modify the starting point, recognizing the timestamp would always be sufficient to solve the problem. But because the training was just working on one particular example, it will typically give the wrong decisions. And so you end up with a high decision regret. So this basically gives some examples of how you can make errors in the recognition, the recognition of the state can lead to 2 types of errors, depending on whether you're really getting information that's too tied to the training example, or it somehow just doesn't really convey the information that you wanted to get if you do it based on colors. Okay. So let's conclude by just looking at what happens in a slightly more complex environment. So clearly we haven't, done the sort of more complex video games, but obviously we want to go beyond the 3-state Markov chain. So here we look at this very simple maze example, where again what we want to do is go to the key, go to the door, and then go to the target, and we want to do this in as few steps as possible. And here we do something very similar to what we had before. We have our training configurations where we just decided to make the colors correlate with where the keys and with where the door is. But then we have, when we actually go to our test environment, we take the colors away. So the color during the training, it's spuriously correlated with the door, but it's not actually critical information. We can solve the maze. A human could solve the maze easily without knowing what the colors were. So we looked at 3 specific agents here, where in the kind of where we just fed this state to a standard RL algorithm, but we did some pre-processing to kind of represent the encoding of the state before we passed the RL algorithm. So the first was we just passed the state as is, along with the colors. The second, we kept the state as is, but we just hid the colors. We made the colors grayscale. And lastly, we actually hid the door. So we just put a door in every place with the state. So what we see here is that with the first one, we're over-specific. We have a high decision regret and a low recognition regret because the agent picked up on the irrelevant information, which was the color. However, if we hid the colors and did the training, then all our regrets were 0. We could get perfect training because, in fact, that sort of shows we got exactly the right amount of information. And then, lastly, if we actually take the door, if we actually take the door out of the state, then things go the other way around. The recognition regret now becomes higher, and the decision regret becomes lower because effectively this representation is not enough to solve the problem. And then lastly, wanted to talk about a version of Pong where we did the following. to the state. First of all, we put a counter on there. So this was information that for a given state would be correlated with the for a given starting point, then the actual times the timer would actually correlate to exactly the game state. But we also put some distraction information on the right hand side. So so here we looked at two sorts of generalization. One was to different initial states. So we gave a random seed to the problem, which made the initial state different. And then secondly, we generalized the different distractions. So we added different random information on the right-hand side. So the game counter was, again, one of these spurious correlations. The distractions were just kind of non-critical to the problem at hand. And so now we get two columns of results, one dependent on one that's affected by whether we should change the initial state, or the second one dependent on whether we add different distractions on the right-hand side. So in each case, we get reasonable training performance. For the case of unseen initial states, I don't think we have the label. If we actually give everything there, it becomes over-specific because we have low recognition regret, but high decision regret. The one where we take out the counter, so again, that shows that the agent maybe sort of hones in on the counter. The middle versions generalize well, where we take away the counters, keep the distraction, or if we take away the counter and remove the random part of the image. However, if we just have the counter, but we change the initial state, then obviously things are going to get very bad because the counter then is not correlated with what we want to do. So here it's under-specific, so we have high recognition regret, low decision regret. If we do the other sort of generalization where we change the distractions, if we change the spurious information, this noise on the right-hand side, then again, for the case we just give the state as is, we get to be over-specific because we have too many spurious things to correlate on. Even if we remove the counter, but we change the distractions, we're still over-specific because we can look too much at what this random noise is, not at what the game is. But in this case, if we just look at the game field or just look at the counter, then it generalized in those cases. So that's basically it. So just maybe to conclude, just let me put up the initial questions again, and I'll leave it to you to decide whether we provided any reasonable answers. But because we see these issues all the time whenever we have an image state, we feel these are interesting questions. Is it when you have these image space states and the RL doesn't work well, is it because it's the computer vision problem that's messed up, or is it the decision making that's messed up? And then lastly, how do we how do we deal with different notions of generalization? What does it even mean to generalize well? And yeah, and should we even use RL? Because I think it's a general consensus that it typically generalizes quite badly for all these various reasons. That's all I wanted to say today. Thank you.
Yeah, I have a question.
Yeah.
Can you go back to the picture where there's multiple doors?
A picture of what, sorry?
With multiple doors.
Multiple doors. Like this?
Yes, that's right.
Yeah.
So in this case, does the key open 3 doors or only open one of the 3?
There is a door. There is one door here in the actual state. This is like the representation. So there is always a real door there, but we're somehow in the encoding, we're giving a bad encoding. You know, this is clearly a bad encoding.
So
the key only opens one door. There is only one door, but we're representing, we're hiding it.
So it's like it's open door at random for the computer. It like it can be being like the key open one of the three doors, but we don't know which one.
Exactly. So I mean, it's clearly a stupid way to do this. It's more sort of trying to be illustrative. I think you should see maybe the point of this work as trying to create some definitions to understand this difference. And this is just an example to show that when you make it under specific, the definitions kind of come out right, that you do, and you work out the regrets, you do actually get, you know, the right way around. You know, now the recognition regret is high because there's no way, you know, if this is your kind of encoding of the state, this is obviously a really stupid thing to do. So the point is that that's kind of picked out by the definitions.
So my question would be like, for enforcement learning algorithm, first do they react to random situation in games or in environment? Does it block completely the learning, or can we negate?
Yeah, I mean, I think that's the question. You know, of course, it depends on a particular algorithm. But I think some of these prior papers, what they've kind of shown is that quite often these agents are not learning what you want them to learn. They're actually responding to things that are completely different. And I think that's different from standard image recognition, because, you know, I think like cats and dogs algorithms now are so good that you can give a completely different picture of a cat it's never seen before. You know, it will do really well. But people actually figured out that a lot of these game playing things, so the lunar lander type of algorithms that Alexander talked about this morning, many times you are training for a very, very specific environment, and you tweak it at all in a way that a human could handle easily, and the RL algorithm goes completely, yeah. And you know, many times you do see it, these game playing algorithms, they're pretty much deterministic. They're saying at stage 12 of the game, take this action, and that's literally all it's doing. It's trying to learn what to do in a given time.
Okay.
Yeah. Good question. So we just use a standard. I mean, these environments are so simple that anything would work well for the training, you know, based on this. But I actually can't remember which algorithms were used for the agents in this case. I don't know, Alihan, if you're still on and can hear us. Can you actually remind me which RL algorithm you actually used for these experiments?
Yeah, sure. I'm not 100% sure that I remember correctly, but I think it was just like a basic implementation of PPO. Like we used the SKRL library, and then PPO was used to train like a convolutional neural network that was also pretty standard, that we just copied from stable baselines.
But I think, you know, the point of these experiments was really to play with these different representations. You know, these environments are so simple that, you know, any RL algorithm in that particular environment will actually train as well as anything. There's probably not going to be too much difference between optimal. Yeah. Question.
It's like this work would allow us to benchmark all kind of reinforcement algorithm, so you can see in point basically how much where basically the error come from, whether it's a representation of action. For example, I know that for policy gradient optimization reinforcement learning, adding some noise can help for the exploration. Did you explore this or not in the work?
Yes, that's a good point. So clearly, yes, adding noise to the exploration. So you always have these epsilon greedy algorithms that do that sort of exploration. I mean, first of all, to your first question, yes. I mean, these are just the definition you can apply to any algorithm. I guess adding noise to the decision is just going to affect your decision regret in some sense. You know, it doesn't really affect the recognition of the state. So it's going to improve the decision regret. That's probably the way to think of it. That so if you're in your if you think of this, that you have your sort of image encoding, and then you have this decision policy, all these sort of notions like taking random decisions and things like that are going to affect the decision policy. So it's going to improve that part of the algorithm, but it's not really going to affect you know, because this is really about how you transform the input into some representation, which you're then going to run your algorithm on. So yeah. Okay. Anything else? Okay. Thank you for coming. And as I say, you know, the majority of the credit for at least the second part goes to Alihan, who just answered the question. I'm less in touch with Xueyuan, so I didn't advertise the link to him today. Okay, thank you.
Thank you.